Welcome back. In this little exercise, I'd like to give you a taste of what it's like to use pole zero positions to design a discrete time filter. In our recent lectures, we've been talking about how the pole zero locations affect the shape of the magnitude and phase response of the system, which we can understand through either the rubber sheet analogy or the graphical method. Today we want to put those ideas and those design rules that we came up with into practice and see how we can change from the world of analysis to the world of actually designing. Now, the technique we're going to use today is a legitimate design technique for particular kinds of filters, particularly the kinds that we're going to be working with today for band pass, band stop filters, and the like. The method is called filter design by pole zero placement, aptly named. So let me set up a scenario for you and we'll walk through this and see how a design experience might go for you. Particularly, we'll look at the case of it's your very first day on the job. As the assistant apprentice product designer, you're all excited and enthusiastic about being there. You're just settled in, getting your first cup of coffee, talking to your new colleagues, getting settled in when in rushes the boss, as they tend to do.
We have a great big problem! We need to ship off the design of our new biorhythmic modulating tensitometer, the thing we call the digital mood ring, to our manufacturing partners by tomorrow. And our design verification testing uncovered that it goes nuts when it gets near power lines and wall outlets. We need this problem fixed right now. And we're already in jeopardy of using up all our startup funds before we get this thing into production. If we have any more delays, we're going to be out of business.
So you try to calm your boss down by assuming a calmer point of view, and you reply, "No worries, boss. It sounds like a classic case of 60 hertz noise coupling, getting into our electronics. I've almost finished Dr. Pilkington's EE328 class, and, I'll just do a quick, digital filter design, slap around some poles and zeros. It will add some new features to the system signal processing software, and the problem's going to be solved. And by the way, can I get a raise if I make this work by tonight?" So the question I'll pose to you is, as a filter designer, before you get down to actually designing anything, what are the pertinent questions that you need to ask, that you need to understand in order to know how to design a filter that will perform the job that's needed? Well, there's a number of things. First, we might ask for a description of what's the noise, what's the undesirable signals or undesirable effects that are going on. What is it that we need to get rid of in terms of signal? Where is it? How much of it is there? What's the basic cause of the problem? And on the flip side, we need to know what are the important signals or ranges of signals that we got to make sure we don't mess up. What is it that has to be preserved after we add our design in, our filter in? And what are the other constraints that are imposed by other parts of the system, and the most fundamental of which is what is the sampling rate of the system? So the kinds of questions we'd have to ask about finding out what those undesirable or noise signals look like. Obviously, we want to know what frequencies do they occur at. Is it one frequency or multiple frequencies? Are they harmonically related, meaning are they multiples of the same fundamental frequency? Those are things we need to know in order to choose the center frequencies for any stop bands or any notches we need to get rid of those particular noise features. We also need to know kind of how wide is the range of around that particular center frequency that there's some noise energy, so we can set up the right width of our stop bands or our notches in order to eliminate all the signal. And sometimes we can't do a perfect job of getting rid of all the noise, so it's helpful to know how much leftover noise, how much can we leave behind if we have to. That sets up a minimum attenuation requirement for our stop band. On the flip side, we need to know about what's the good stuff. What is the range of signals and the type of signals that the rest of the system is reliant on that we really can't degrade. So what range of frequencies do we need to preserve and not filter out, so that if we're creating up any pass bands, where are those, what are their widths, where are their centers? And really need to know how close are critical frequencies that we need to preserve to the frequencies that we're trying to get rid of, because that will set up for us requirements for how wide the noise removal notches or stop bands are that we're going to design. Other system constraints that come into question, obviously, first we said the sampling rate is something we need to understand and know. And are there any other limitations that the rest of the system places, are there any other requirements that the rest of the system places on our addition to it, particularly around delay and phase error, and most particularly if we are part of the internal workings of a closed-loop control system, then any phase we add to the system may be critical. We need to understand, are we allowed to distort the magnitude at all? Do we have to have flat magnitude responses? Can we add a little ripple to it or not? How uniform does the magnitude response need to be in the ranges of frequencies that we're trying to preserve? If we're doing a real-time implementation in signal processing, then we're absolutely constrained to designing a causal system, and of course probably want a stable system. So we have a couple of fundamental requirements that we're going to need to understand. Now, in the real world, unfortunately, typically when this kind of thing hits, the boss says, "We don't have time for all your questions. Just get started. We'll try to get you some answers as soon as possible. And, by the way, we'll see about that raise after we see how well you do at fixing our problem on time." And off he goes. All right, so you set to work. Try to jot down what are some requirements of this filter. Well, we're thinking it's 60 hertz noise, and you probably would want to do some confirmation on that. You would want to make some spectrum measurements on some signals that you see when the problem is present, and make sure that when the problem goes away, that signal is gone. If you determine, and it certainly sounds like this is the case, that it's 60 hertz noise getting into electronics, we probably want to notch out the range of frequencies around 60 hertz with a narrow notch bandstop filter that's going to eliminate the magnitude response down right at 60 hertz and go back up pretty quickly. Our sampling rate, it turns out we find out, is 480 hertz. The notch frequency then we want is 60 hertz. To turn that to a digital frequency that we're going to design that notch for in a discrete time filter, we would normalize the analog frequency 60 hertz by the sampling frequency 480 hertz and find that the frequency we want to notch out in a digital filter is at 0.125 cycles per sample. All right, well, so we get to thinking, what kind of filter should we design? Well, let's start with an FIR filter. They're always safe, they're always stable. I can even make it linear phase if I want, which everybody tells me is really nice. And I know they're going to want it causal, so that's not hard to do with an FIR filter. So, okay, let's do that. Now, we want to put a notch in. We want to eliminate some frequencies. So, sounds like what we're going to need to do is use something that pulls down our response. That calls for probably a 0. In that, at wherever 60 hertz is in our Z domain, we want the magnitude response to be 0 at that location. Now, where is that location? Or where is 1/8 cycles per sample in frequency response? Well, recall the relationship between h of z and h of f is h of z is h of f, where we replace the angle in the z domain with 2 pi f. So we're finding points on the unit circle. All the points that make up the frequency response of the system are what happens above the unit circle in the z domain. So if I want a 0 response at frequency 1/8, I need to go to an angle 2 pi times 1/8, which is pi over 4, measured from the horizontal, from the positive real axis of the z domain on the unit circle. So we'll rotate up here to pi over 4. So there I'm going to want a 0. Okay, so that's where 60 hertz lives on in my z domain when I have a sampling rate of 480 samples per second. Now, that's not the only place I need a 0. We know we want real values real number values in our difference equation and transfer function. That requires us that whenever we have a complex polar zero, we have to have its complex conjugate along for the ride as well. So I have to have that. I have to put another 0 at minus pi over 4 on the unit circle. Now, is that all I need? Well, no. I want a causal filter. The requirement for a causal filter is I have to have at least as many poles as I have zeros. So if I have 2 zeros, I'm going to need 2 poles somewhere. But I also want the filter to be stable. And if it's causal, to be stable, those poles have to be inside the unit circle. And if I want an FIR filter, a non-recursive filter, there's only one place all of my poles are allowed to be. That's at z equals 0. So if I need 2 poles, I need to put them both at z equals 0 to have a non-recursive filter. And I've got a nice notch at 60 hertz, or 0.125 cycles per sample. This looks like a promising filter. So let's run it through our MATLAB analysis. We do a little freak Z on it. We run it through the rubber sheet analogy, and we see that, sure enough, I've pulled down the rubber sheet where I wanted to, pulled it down to 0. It's given me a frequency response minimum in zeros right at the frequencies I want. But my magnitude response is kind of wonky here. I've got these high wings here at above 3 at the Nyquist rate. I'm only coming up to a height of about 0.6 in between. I really would like a uniform notch that has a gain of 1 everywhere, except right there at 60 hertz, and a much narrower notch. This one's way too wide. It's just very slow and sluggish, pulling down the rubber sheet and then rebounding way too much. I do have linear phase. That looks good. But while I've notched out the right frequencies, I'm probably throwing away way too much of these other frequencies and boosting up these other ones disproportionately. So good start, but we're not there yet. And of course, just as you're realizing that, that's when the boss walks back in and said, "Hey, good news. I have some information for you. But, whoa, looks like you're done. That's great. Hey, wait a minute. Wait a minute. That's not going to work. We need to be able to sense slow changes in mood. Do you even understand how this thing works? That happens over a period of seconds and minutes. We need really good low-frequency response, and your stupid filter would destroy all of the low-frequency sensitivity of our system. Look at that. Got no gain down there at low frequency. I thought you said you knew what you were doing. Oh, and by the way, we did just discover that it's not just 60 hertz noise running around our system, but when we finally put some oscilloscopes and spectrum analyzers on it, we saw that it's not just 60 hertz, but all of its harmonics. So you better filter those out as well. So now get back to work and try to do a better job this time. So we've got some, not just 60 hertz, but we've got some smaller spectral peaks at all of its multiples. So, all right, the one notch is not going to do, and we got to do something about that width of that notch. So first, how do we get those harmonics? Well, just like we did before, we need to find those frequencies on the unit circle, and those will be happening at integer multiples of 60 hertz. So we'll need one for 60 hertz. That was our one at pi over 4. We'll need one at twice that frequency. So we normalize 120 hertz by 480 and get a frequency 1/4. Go to 2 pi times 1/4. That's pi over 2, or 90 degrees. And we'll need its conjugate at minus pi over 2. 180 hertz normalizes to a frequency of 0.375. 2 pi times that is 3/4 pi. Again, plus or minus to get the complex conjugates. And 240 hertz, which is the Nyquist rate, is frequency 1/2, which is over there at z equals -1, or an angle of pi. Beyond that, well, we're above the Nyquist rate, so those are all the harmonics we can really eliminate in our system, the only ones we need to worry about. So we're going to need zeros in all these positions. we've got them at plus or minus a quarter. We're going to need them at plus or minus a half, plus or minus 3/4, and over there at pi. And I'm going to need to match all those zeros with poles if I want to keep it FIR. So if I have a total of 1, 2, 3, 4 4 zeros now, plus and minus on these. So 2, 4, 6, 7. I'm going to need 7 poles. And they all have to be still at z equals 0. So there's a pole zero diagram for that filter. It's still FIR. It is going to notch out 60 hertz, 120, 180, 240. And actually even the higher ones. When we plug it in and do our analysis, we see, yeah, we got the nice notches where we want them. They're a bit narrower, but I've also got some kind of weird shape in my magnitude response. Because I don't have a 0 over here at DC, I don't have things kind of equalized, and so there the gain is allowed to go up really high compared to the other locations. So that's not quite going to work. We still have linear phase, so that looks all right. So what are we going to do? We need to equalize the gain here outside of the notch. We need to bring this one down. We need to bring these up a little bit. Well, if I need to pull things up, I can't do that with zeros. I have to do that with poles. And if I'm going to move poles around, the first thing I have to do, if I'm going to move any of them off of this z equals 0, I'm giving up the FIR filter. As soon as I move even a single pole off this z equals 0, I now have a recursive filter, and it's likely to be IIR. Well, let's accept that. So I'm going to need to put some gain at higher frequencies and drop the gain at low frequency. Well, right now at low frequencies over here, these poles are pushing up the rubber sheet way high, and these zeros are dragging down the rubber sheet on the other side. So I might surmise that I probably need to move a couple of these poles this way towards the high frequency side to boost up the gains over at higher frequencies and give less boost to the low frequencies. So let's try that. Let's grab 2 poles, shift them back on the real axis, still leave 5 in the middle, and you'll notice we did bring down the center and start bringing up the high frequencies if we compare that to what we had before. And now after we're kind of going in the right direction, we're giving a bit too much emphasis over here to this one, this notch here at the Nyquist rate caused by this. So we're getting kind of close to this part of the unit circle, causing that to be boosted more than we are over here between some of these other ones. So we might start thinking about, well, let me move these poles off the real axis and kind of move them a little bit more closer to some of these ranges that need more boost. And maybe let's bring some more back too. While we're playing with that, of course, the boss walks in while we're dabbling and said, "What's with the bat ears on those magnitude response?" And oh, by the way, did I not mention that we also need to still detect increases in heart rates that are normal so we can tell when someone's getting excited? How else are we going to make the mood ring change color? So you better not filter out too much from about, 70 hertz up to about 150 hertz. Except, of course, those nasty line frequency harmonics at 120. So come on, hurry up. We got to get this going. Unfortunately, that's kind of the way it goes. And if you don't have all the information up front, it comes out in dribs and drabs and affects your design. Just when you think you're on the right track, something new comes in and sends you off in another direction. All right. Well, we still need to equalize these notch heights. We still want the notches there at the harmonics. We want the magnitude response kind of leveled off, and we probably need these notches to be narrower. And so, and we just found out that the signals from 70 to 150 hertz have to be pretty much near a gain of 1 and unaffected. Now, that means we're going to want a flat magnitude response from about 70 hertz, which we normalize and find that's at about 0.146 cycles per sample. And 150 hertz is about 0.3125 cycles per sample. So in our diagram here, from 0.146 up to 0.3 something, we want that range to be pretty flat, which it's not right now. So we've gotten rid of the right frequencies, and for these kind of filters where we're trying to get rid of very specific frequencies, creating a notch kind of filter, this pole zero design technique is actually pretty good. We can choose the stop band centers by choosing exactly where we locate our zeros and place those on the unit circle at the right angle, which we did, so that much is good. Now, in these kind of filters, if we want a narrower notch, a narrow transition band, the trick is that we need to bring poles out along the same radius that the zeros are, and the closer we bring those poles to the zeros, the narrower the notch gets. Kind of a rule of thumb is the 3 dB bandwidth we'll achieve in digital frequency. If we want to achieve a certain bandwidth, delta sub f, we would place the poles at the radius 1 minus pi times delta sub f, where delta sub f is in cycles per sample. So if we spread out our poles along the same radii as our zeros, got them away from z equals 0 and started doing that, you'll see we've gotten the notches a little bit narrower. The poles are also helping make the tops of these peaks a bit more uniform, although not having a 0 here at DC is still giving me an extra bulge here as the rubber sheet's not pulled down at that point. If we move out a little further, notice that the notches get narrower. If we go out even further, they get even narrower. And notice too that my magnitude responses are also getting more uniform as the poles are starting to pull everything up and make them pretty close to 1 everywhere. If you can go to some extremes like 0.98, just right behind the zeros, we get some very narrow notches. And we could take that even to a higher extreme, 0.99. At some point, we're not going to have enough notch width to actually take out the frequencies that we want. So we probably want to back off a little bit from here. But this is a classic way to create an IIR notch filter. We drop the zeros at the locations that we want to be notched out. We put a pole nearby it, maybe not quite so close, but nearby it to get, and its radius will control the width of the stop band. So again, looking at those options, there's 9.99, 0.98, 0.95 gets much wider, 0.9 even wider still. And so we can control the width of the path of the stop band by controlling the position of the poles relative to the zeros, how far out in the radius they are. And back comes the boss. Okay, you finished? Hey, that does look like a nice filter. That should really kill those line harmonics. But guess what? We just discovered something else. We also kind of need to filter out some other noise that showed up in the testing at higher frequencies, like above 180 hertz. There's a pretty strong noise spike around 210 hertz that you'd better totally kill. But don't screw up the signal below 150 hertz. And oh yeah, keep hurrying up. Okay, so the requirements are getting a little crazy now. This is where this design technique begins to become a little bit less definitive. For placing notches, it's really good at that. For creating other shapes like low passes and high passes, or to tailor the shape of the frequency response, it becomes a much more qualitative seat of the pants technique. It's kind of guess and check, try things out, move things around, see what works. So if in addition to everything else, we need to get rid of frequencies above 180 hertz. So I need to add a low pass kind of feature here, getting rid of more of the high frequencies above 180 hertz, which happen to be at an angle of 3/4 pi. And by totally filtering out, there's a bad spike at 210 hertz that we want to make sure we completely get rid of. That's at an angle of 7 pi over 8. But while we're eliminating things above 180 hertz, by the time we get down to 150 hertz, we need the magnitude response back up close to 1. And so we need a fairly narrow transition from that stop band to the pass band. And we want pretty flat response from 150 hertz down, except for those harmonic notches that we created. 150 hertz happens to be at 0.315 cycles per sample. So to do this, what are we going to do with that pole at z equals -1? Well, this one that's holding up the rubber sheet here, that's helping create the narrow notch here, but now we're saying we want to filter out, we want to remove some of these high frequencies. So the first thing we'll do is remove that pole. And let's drag it all the way back here to the 0 so it doesn't do much of anything else. And as happens with this technique, when you do something that seems fairly obvious and straightforward, it changes everything else. So without that pole out here, this 0 drags down the rubber sheet and affects all these other frequencies as well, reducing their magnitude response. So now what do we do? Well, we can add a couple more zeros out here to do a better job of filtering out those high frequencies we want to get rid of. So we can drag down things to make sure that these upper frequencies are gone like they're supposed to. But I'm going to need to push things back up over here at these frequencies to get back to the passband that we wanted to preserve certain frequencies. And so for that, maybe we'll bring some poles out that way to try to bring up that side of the rubber sheet. To balance things out, we're probably going to do better by splitting those off closer to the zeros. Maybe move them out a little closer. And here's where you're kind of playing. You're using your best intuition and understanding of what might work, moving your poles and zeros around. There is no one correct answer in this kind of a design technique. It's very much trying things out, playing with it, manipulating it till you get something that meets your specifications. Now, that's not to say this is the only way that we have to design digital filters. There's actually a number of deterministic ways. There's several techniques for designing FIR and IIR filters that we can target certain design requirements, build that into our design, run it through the process, and get what we were asking for. This particular filter is kind of a combination of different kinds of filters, and using this pole zero technique, it's again much more qualitative, much more seat of the pants, not as deterministic. So we keep having to tweak it until we have something that's usable. This is where a program like MATLAB is extremely helpful. If we have the analytical tools to try something out, see what effect it has, we can go through these iterations much more quickly than we could trying to build something in software and trying it out that way. This we might manipulate, play with it, keep playing with those pole positions. Looks like we moved him a little bit further out, but that was too much. So we got too much gain out here due to this pole getting too close. So we back it back off a bit, play with it till we get this magnitude response pretty flat over the range of frequencies we want. And now it's starting to look like something like what the boss asked for. We've got our harmonics knocked out. We've got the high frequencies filtered out. We've got a pretty quick transition up to a uniform passband except for those harmonics. So starting to look pretty good here. And in walks the boss, who agrees. Said, hey, that looks like that filter just might do the trick. So, okay, run that design over to the software guys, see if they can get it implemented right away. And, oh yeah, you can stay tonight, right, to get it implemented before we go into production tomorrow. And, oh, we'll talk about that raise after you help us solve this other problem we just discovered. And that's kind of the way it goes sometimes. So you've seen some of the design rules that we came up with in class for filter design put to work. Again, this is a legitimate technique for designing some kind of filters, particularly notch filters, some bandpass kind of filters. but it's not the best way. It's good for those, but there are, again, a number of different techniques. If you want to learn those, we do have other courses to do that. EE 419, 459, digital filter design. And we have a graduate course, EE 515, teaches advanced courses. Some of you have used one of those techniques already so far or are about to use it in your EE 368 section, FIR Design by Windowing. There's a number of techniques. I hope you've enjoyed seeing this one and maybe getting a taste of what life might be like out there in the real world. Not really that bad, but kind of fun, I hope. So with that, we'll let you go for now. Take care.